All right, welcome everyone. Today's lecture is over chapter 7, energy transfer during physical activity. So this is where it's going to get fun, I think. So the last couple chapters were sort of boring, um, concepts that are really hard to visualize because it's hard to think about what's occurring inside of a cell. Am I right? It's so small. It's a very abstract concept. Now, however, we're going to apply those things and think about them in the context of actual physical activity. And we're going to be on this theme for the next few chapters. So when you think about exercise science, exercise physiology, this is really what it's all about, right? You have to do some background in terms of anatomy and physiology to learn about how energy is produced. But once you lay that foundation, now we can get into some of the more interesting and fun stuff, I think. Okay, so I want to reiterate something that we touched on last chapter, and that's that the three energy systems that we learned about. So we have the phosphocreatine system, which is also known as the immediate. We have our glycolytic system and our aerobic system. They all three are always contributing ATP, right? The question is, how much are they contributing? So you notice, like, these are two graphs that I really love, and there's another one on this slide as well, but we'll focus on these two first. What this shows you, let's start over here. The dark gray is phosphocreatine system, the black is glycolysis, and the dark gray is aerobic. So you notice, even in the first 10 seconds of exercise, even though the phosphocreatine system is the primary supplier, so about 75% of the energy comes from that, you still get a small contribution from the glycolytic and the aerobic. Okay, as we then move on to the 30-second time period, the primary contributor now is glycolysis, as we've talked about, and that continues for the 60-second period as well. But we're still getting some contribution, from phosphocreatine here and aerobic here. As the time moves on, percent contribution from phosphocreatine drops, okay? And maybe by the time we get to 2 hours, we're not getting any from that, but it's pretty rare that we exercise for 2 straight hours. So even in an hour, where's the hour? We're still getting a tiny, tiny bit of phosphocreatine. But as that time increases, also glycolysis starts to diminish, still is contributing, but the percent contribution is shrinking. While at the same time, the contribution from aerobic metabolism is increasing to where by the time you get like beyond an hour, the vast majority, over 90% of the energy is coming from aerobic energy production, right? So it's, again, I've said this before, it's not an on or off switch. It's more like a dimmer switch that as exercise duration moves on, you're dimming the anaerobic contribution and you're increasing the brightness on the aerobic contribution, okay? This graph here shows the exact same thing. It's just another way to look at it. The solid black line is the phosphocreatine, so it peaks at 10 seconds and then it drops pretty rapidly. Glycolysis starts off slow, it increases and peaks at 30 seconds and it stays high up to 2 minutes and then it starts to tail off, while the aerobic system has a lag to it. It starts off very low, slowly but steadily increases to where it takes over as the primary supplier, sort of at this crossover point here, at around somewhere between 2 to 5 minutes, okay? Now, there are some implications for this, as we'll talk about later in this lecture. When we're relying on glycolysis, as we are here, we're not getting a lot of ATP, because you remember you only get 2 ATP per molecule of glucose from glycolysis on its own. We also are left with lactic acid, which, if it accumulates, is a bad thing. It causes us to feel fatigue, right? So even during low to moderate intensity exercise at the beginning, we have to rely on glycolysis, and that kind of puts us in a hole. You might have noticed when you start exercising, even if it's not an all-out activity, you're a little bit winded at the beginning. For the first couple minutes, you feel a little bit winded, but once you settle in to that activity, your breathing rate drops a little bit and you feel a little bit better, okay? What that is showing us is that reliance on glycolysis in the first couple minutes leads to some lactic acid production, and that's why our breathing is elevated above what it should be given the intensity of that activity. Okay, so remember I said that there is a price we have to pay for this, and we'll come back and talk about that in a little bit. Sorry about the sneeze, and I'm trying to fight it off. In Kentucky, where I live, the allergies are really bad because we live in a valley. So all of the pollen and stuff just settles in the valley, and it makes us very allergic here. All right, so, and this is another, I just left this graph in, this is stating the exact same thing. This is actually the one from the textbook. I just like these two a little bit better because they're a little simpler. This one shows the exact same thing, so I'm not going to go through it again. But again, look at this one, try to compare. All three of these graphs are saying the exact same thing. So maybe one appeals to you and you can understand it a little bit better. So take a second to look at all three of them and to understand that we're on a continuum here, okay? Continuum means it's like a broad spectrum. It's not like this or that, it's everything in between, right? So depending upon the time of the activity, the intensity, we're going to be at various places on the energy system continuum, but all three will always be contributing. The question is, what is the primary contributor to ATP production? Okay, so we're going to sort of review these quickly. The energy systems again. So the phosphocreatine system, again, this is the primary supplier for activities that are very short duration, less than 10 seconds, okay? When you need energy immediately, this is where it's gonna come from. So I made a list of activities, and this is kind of a review for us as well because we've already done this, but these are some activities where almost all the ATP required to fuel these activities I have listed here will come from the phosphocreatine system. A 50-yard dash can take you anywhere from 5 to 10 seconds, right? So all the energy that's a short burst activities come from this system. An Olympic lift, which something like the clean and jerk, the snatch, where you're moving a barbell from the floor over your head rapidly, that takes seconds, maybe like 1 to 2 seconds. Again, that's going to all be this system. A broad jump, again, is just a couple seconds. Even something like hitting a baseball, hitting a golf ball, the tennis serve, any sort of explosive activity. Explosive activities require immediate ATP. This system, that's why it's called the immediate energy system, because it immediately supplies ATP to fuel these types of very short duration activities. Now, if the activity extends in duration into that 30-second to 2-minute range, such as activities listed here in blue would do, so a 400-meter run, I guess depending upon how fast you are, some of you may run track and might think I'm stupid when I say this, but I don't know, 50 seconds up to 75 seconds, maybe it would take somebody to run a 400 depending upon how fast you are. And 800 is 2 laps around a track, maybe that's like 2 minutes or so. Well, then there's swimming events. I'm not super familiar with the time it takes to swim certain distances, but a lot of swimming events are going to rely primarily on glycolysis for energy. Okay, and as I mentioned earlier, when you're relying primarily on glycolysis, as you are during this time frame here, there is going to be lactic acid formation, right? Lactic acid forms when pyruvate and hydrogen cannot enter into the aerobic energy systems. They have to go somewhere, so they combine, and that forms lactic acid, okay? Now, the longer that activity goes at that high intensity, the more lactate is going to accumulate, right? So if you've ever tried to run, an 800 tends to be the worst, I think. If you've ever tried to run an 800 as fast as you possibly can, there's a lot of pain associated with that type of distance, right? And that's because the prolonged nature, you're really pushing the envelope of this 2-minute all-out activity here when you're running an 800. So your body's just producing tons of lactate. That lactate is accumulating, and lactate stimulates pain receptors. It also makes us very out of breath because there's a lot of, as we'll see later, lactic acid can be converted into CO2, which you can expire, and that's why you hyperventilate when you have a lot of lactic acid building up in your body. So the only way to slow down lactic acid accumulation would be to slow down on the run, reduce your exercise intensity, or stop in general, right? So if you're doing an 800, you finish, lactate is high, you start walking immediately or even slow jogging, lactate is going to be cleared very rapidly. In fact, active recoveries actually can lead to more rapid clearance of lactate, as we'll see here in a few slides. Now this is kind of showing you what I mentioned earlier, right? When oxygen is not available, as it is not during this short-term activity, right? It takes a while for oxygen and for our aerobic energy system to fire up. So during that 30-second to 2-minute time period, we say oxygen is not available, okay? So, as we mentioned, these pyruvates here and these hydrogens that are bound to the NAD, they cannot go to the Krebs cycle and the electron transport chain because oxygen is not available. So the only other option is to combine with each other to form lactate, right? Now that's only for an all-out type of activity. When you're doing aerobic exercise and the intensity is less, say it's like if you're running all out as 100% intensity, let's say you're exercising at like 60% intensity, lactate is not going to accumulate as fast, and you don't feel those feelings of pain or fatigue like you do when you're exercising all out, right? So again, it's a continuum. Your intensity very much determines where you are on the energy supply continuum, okay? Now let's talk about lactate for a little bit, okay? So as I just mentioned, blood lactate does not accumulate at all exercise levels. It has to typically be a moderate to high intensity activity, okay? Some people might say that is at an intensity of 50% of your aerobic capacity. Here in a few slides, we're going to introduce a concept known as VO2 max, okay? That's your aerobic capacity. 100% of VO2 max is like all out effort, okay? So 50% of VO2 max is like half effort, okay? So typically with activities that are at 50% or less of your VO2 max, there is no lactate accumulation, okay? So this is an important point. This is another one of these like foundational exercise physiology concepts. I'm going to jump back again. I know you probably get frustrated when I do this, but this is for a purpose. Now, since we always have some glycolytic contribution, there is always going to be lactate production, always. However, when your intensity is lower, lactate is cleared at an equal or even a greater rate. So even though you might be producing lactate, your body is clearing lactate out either just as fast or even faster than it's produced, okay? So when clearance is greater than or equal to production, there is no accumulation, right? Lactate only becomes a problem when it accumulates. That's when we experience fatigue, pain, etc., okay? So at low exercise intensities, this is the situation that exists. We're producing lactate, yes, but we're clearing it faster than we're producing it, so it does not accumulate, so we don't feel anything, right? It's not a problem. At higher exercise intensities, and this varies greatly upon the person, right? The more fit you are, the higher the exercise intensity this occurs. The less fit you are, the lower intensity. Let's just say your average population, not fit, sedentary people, at exercise intensities above 50 to 55% VO2 max, production now flips and is greater than clearance or disappearance. These two words, you could use these interchangeably, okay? Shoot, sorry about that. So in production, when you're making more than you're removing, it accumulates, right? Let's kind of imagine, like, what does that look like? Well, let's say that it's fall, you have a giant oak tree above your head and it's super windy, all the leaves are dead. You're raking the leaves, but the leaves are falling out of the tree faster than you can rake, so this huge pile of leaves is accumulating, right? So that's kind of what the situation that we have occurring right now. There's more leaves falling than we can get out of the way, so this big pile accumulates under the tree, okay? So let's talk about that a little bit more. There's a point at which that occurs, okay? And what we call that is the lactate threshold, okay? So again, this is another one of these concepts that is sort of like one of the key concepts in exercise physiology. So we could define the lactate threshold as what we see on this bullet point here, the point at which lactate begins to accumulate in the muscle and or the blood, okay? Lactate is produced in the muscle, but it can enter into the blood. So you, if you measured lactate, you measure it from the blood, right? When we do lactate threshold testing, and we'll do one of those labs later in the semester, we sample the blood and we measure the lactate in the blood as a reflection of the lactate that's in the muscle. Muscle will have higher concentrations of lactate, but you're not going to jab somebody in the muscle to sample the blood. You just sample their venous blood, okay? So these are graphs that we use a lot in exercise physiology. So on the bottom, this represents exercise intensity. Now I mentioned a second ago, often exercise intensity is described as a percent of your VO2 max. Your VO2 max is your individual aerobic capacity, okay? 100% of your VO2 max would be you exercising all out as fast as you can, as long as you can. And I did this arm motion because I'm imagining like I'm running. 50% of VO2 max would be like half effort, right? 25% would be quarter effort, 75% three-quarter effort. You get the idea, okay? So notice here, with untrained subjects, the lactate threshold typically occurs at around 50% of VO2 max. Now what we're looking at, like over on, the exercise intensity is on the x-axis, blood lactate concentration is on the y-axis. So as exercise intensity increases, blood lactate concentration is going to increase in a linear fashion up to 50%. But once we get to that 50%, in an untrained population, now production is going to start to outpace clearance, which is going to lead to, what's the magic word? Starts with an A, accumulation, okay? And that accumulation is displayed graphically by this sort of dramatic slope that lactate concentration now takes, right? So it's nice and smooth here. Accumulation is not occurring, but once we get to this exercise intensity, now the person is relying more on glycolysis for energy production. So lactate production goes up, lactate clearance goes down, accumulation now occurs, the lactate curve shoots up, okay? Now, this is where being in shape is beneficial, right? If you're fit, okay, so in a trained population, the whole lactate threshold curve can move to the right of the graph. So notice in a trained population, their lactate threshold may not occur until 75% of their VO2 max. So they can exercise at a much higher intensity before accumulation begins to occur, right? And they can also withstand much higher concentrations because, you know, it's kind of like you build up tolerance to pain, right? The first time you, I don't know, get hit with a baseball, it hurts a lot, right? But if you play baseball, you probably get hit with a baseball a lot, so you kind of get used to that pain. Same thing happens with lactate. When you're not fit, you're not accustomed to having high lactate levels, it can make you feel sick, it can make you feel acute pain. But if you're somebody who trains all the time, you probably get used to that pain, right? Like if you're a track athlete and you run the 800, you're accustomed to feeling that discomfort, right? That's what you do. So you can tolerate higher levels of lactate, which is why ultimately not only can a trained person exercise at a high intensity without feeling that discomfort, but they can also tolerate higher, they can accumulate more lactate without, again, having negative effects, okay? So last thing on this, the practical implications of this. If this was two individuals, we had our yellow athlete and our red athlete, and they're both running a 5K, which is a 3.1 mile race. Who's going to be able to run faster? Red or yellow? Well, obviously the red. Even if they had the same aerobic capacity, let's say they had the same general VO2 max, the red athlete can run at 75% of his or her VO2 max, which might be 10 miles per hour, where the yellow athlete can only run at 50% of his or her VO2 max, which might be his 8 miles per hour. So if one is running at 10 miles per hour and the other is running at 8 miles per hour, who's going to win that race? Obviously, the red athlete is going to win. Okay, so and as I say on this last bullet point, it's not uncommon for people to get their lactate thresholds up to 80 to even 90% of their VO2 max. Right? Like I'll use the example of if you run the 800 again, you have a very high lactate threshold. I guarantee it. I've tested my own personal lactate threshold. I run some. My lactate threshold is upwards of like 90% above my VO2 max as well. A simple way to do that is to run a lot of hills. If you run a lot of hills, you're going to generate a lot of lactate going up those hills. So if you train hard on hills, you can really improve your lactate threshold to a much higher percentage of your VO2 max. Okay, let's move on. Well, I just sort of gave away this slide. How do we improve our VO2, our lactate threshold? Well, it improves for a few reasons. First of all, you by forcing your body to rely on carbohydrate for fuel, which if you do a lot of anaerobic exercise, it will do, your body starts to store more carbohydrate in the muscle. Okay, carbohydrate is stored in the muscle in the form of glycogen. Glucose is an individual carbohydrate molecule. Glycogen is like a bunch of glucoses stuck together. In our muscles, we store glycogen. We also store glycogen in our liver as well. Okay, intramuscular glycogen stores will increase with training. So the more intense training you do, the more carbohydrate you'll store in your muscle, and that means you have like a larger gas tank to fuel your engine. Okay. Then we also, those enzymes that we saw that run the glycolytic cycle, when you do intense training, your body produces and retains more of those enzymes. The more of those enzymes that you have, the faster glycolysis can cycle and the more ATP you can produce, right? Okay. I don't know what they mean by improved motivation during training, because this type of training hurts a lot. However, when you finish it, it is sort of like invigorating, I guess you could say, but it's also mentally draining. So maybe what they mean is you have to be motivated to do this type of training, right? All out exercise requires more motivation than submaximal exercise for sure. So some examples, I gave you hill running. That's an example. If you get on a bike, like a stationary bike or the Airdyne bike, which are the type of bikes that have the arm crank as well, and you do 20 to 30 second just all out sprints on a bike, that's a good way to improve your lactate threshold. Not just running hills, but even flat running sprints. That's another good way to improve your lactate threshold. Suicides, which are, activities that a lot of basketball, soccer players do. That's basically just sprinting back and forth as fast as you can. You get the idea. The intensity has to be all out for periods of 20 to 60 seconds. That's the type of thing that improves your lactate threshold. But as I said, that's not fun and it's gonna hurt. But the payoff is shifting this curve to the right, and that's gonna make you a better competitor, to be totally honest. Especially if you're in a sport that requires a high intensity. Okay, so let's jump now to the aerobic system. So as we saw, I'm going to jump back to my graph again. The aerobic system is contributing some right away, but not very much. But as time wears on, the contribution of the aerobic system is steadily increasing. The glycolytic system is great because it's fast, okay? But it doesn't give you much. It's inefficient. The aerobic system is great because it gives you a lot. It's very efficient. The downside is it just takes a little bit more time to get ramped up, okay? So it doesn't really get ramped up until 2 minutes and beyond, right? So even though it's giving you energy early, it doesn't really start giving you energy until you get beyond 2 minutes. So if you're an 800 runner, you're not using your aerobic system much at all, okay? But if you run the 5K, which again is 3.1 miles, most of your energy is coming from the aerobic energy system. If you run the marathon, most of your energy is coming from the aerobic system. So as we say here, oxygen intake is going to steadily rise, okay, and then it's going to plateau, okay. So if we're running something longer duration, such as a 10K, which is 6 miles, a half marathon, a marathon, we're eventually going to reach this point that we call the steady state, okay. Steady state, in the book uses steady rate. I use steady state. I changed this word to state in most of the slides. Here's one that I already forgot, but just know steady rate and steady state, they mean the same thing. Steady state is the term I've always used. I don't know why they use steady rate, but they mean the same thing, right? So during long-term exercise, especially if you're fit, you should reach a point where you're at a steady state, okay? So what does a steady state really mean? Okay, imagine when you're at rest, your heart rate is stable at, let's say, 60 beats per minute, okay? As soon as you start exercising, though, your heart rate's going to start increasing up over 100, okay? Rather than it continuing to increase all the way to your max heart rate, if you're doing submaximal exercise, submaximal just means less than maximal. If you're doing submaximal exercise, eventually your heart rate's going to reach a point where it's going to start to plateau. And let's just say, for sake of argument, that's 120 beats per minute. Once your heart rate gets to 120, it's going to stay stable. As long as you keep running the same speed, biking the same speed, swimming at the same speed, whatever it is, your heart rate's going to be elevated, but it's going to be stable. Okay, and that's probably the best way to describe a steady state. A steady state is when your metabolic, your physiological functions, I should say, heart rate, breathing rate, energy production, they're elevated above resting, but they're stable. That's a steady state. Theoretically speaking, you could maintain steady state exercise for a very, very long time because there's no lactate accumulation. Notice here, the energy required by muscles is being met by aerobic production reactions, meaning there's very little glycolytic contribution, which in practical terms means there's no blood lactate accumulation, okay? If you're doing steady state exercise and you're relatively fit, there should be no lactate accumulation, which means you should theoretically, and this is not true, but theoretically, you should be able to continue that exercise indefinitely, right? Now, obviously, we can't do that, but you get the idea of where I'm going, hopefully. Now, we're going to introduce two concepts here. Okay, we're going to have what we call the oxygen deficit and then the epoch as we close out this discussion on aerobic metabolism. So earlier we showed that it takes about 2 minutes for the aerobic system to really ramp up and start becoming the primary supplier. Now, prior to 2 minutes, you're still going to need ATP. Okay, so that ATP is going to have to come from anaerobic sources. Okay, even if you're doing light intensity exercise, you're still going to have anaerobic energy production dominating in the first 2 minutes. Okay, so we like to graph that using this is kind of the classic oxygen deficit graph, and that period of time under 2 minutes when you're relying on anaerobic energy production is what we call the oxygen deficit. and that is represented by the orange block here in the graph, okay? Now, much as training influences the lactate threshold, training also influences your oxygen deficit. People who are more fit, they can make that transition to aerobic metabolism faster and easier, so they accumulate a smaller oxygen deficit. So notice the yellow line is the trained individuals. They transition to aerobic energy production faster, where untrained people takes a little bit longer. It's not a huge difference. You're talking 30 seconds maybe. However, that's 30 seconds of lactate accumulation that might occur in an unfit person, right? So that's a key point. Probably is during this period, some lactate accumulation might be occurring until we can transition to aerobic energy production. The less lactate accumulation that occurs, the better for us. So the fact that fit people or trained people can transition to aerobic metabolism faster means they have less lactate accumulation, so they're able to achieve that steady state faster and basically have less fatigue going into that steady state, which means they're going to be better able to perform whatever activity that we're doing here. On the other hand, the untrained person, they might have a little bit more lactate accumulation that occurs during the first 2 minutes of exercise, so they're going to be in a bigger hole once they reach the steady state period versus the trained person. So they're not going to be able to run as fast, swim as fast, bike as fast, etc. Okay. So again, I'm gonna focus back again on the steady state for a second, and then we'll come back to the oxygen deficit. So once we reach this point where all of the ATP we need is coming from aerobic sources, again, theoretically, we could do that indefinitely. Now, of course, we can't, and there are limiting factors. You know, eventually, if we exercise for multiple hours, we're going to have electrolyte depletion. We're going to have fluid loss. We could replace our fluids through drinking water, drinking Gatorade, etc. If we can do that, again, we can continue exercising for many hours. Okay, you hear people running ultra marathons, which are like hour-long activities, right? On the other limiting factor might then be fuel. Okay, so do you have enough glycogen stored in your liver and in your muscles to power exercise? You know, during most activities, this is not ever going to be challenged. If you get to, you know, running a marathon and beyond, then you might get into the point where muscle glycogen starts to, and liver glycogen start to become depleted. But for most of us doing basic exercise activities, neither one of these are going to be a factor. What's going to be the limiting factor for steady state exercise is our motivation, and then musculoskeletal limitations, like our muscles get tired, our joints start to hurt, and we just don't want to exercise anymore, right? Because theoretically, we have the fuel, we have the fluid. If we have those two things, we could exercise indefinitely, but of course, we don't usually do that because of the factors I just mentioned. So people who can maintain steady state for long periods of time, usually they have a couple key factors, okay? And to jump to the last point and then work our way backwards, people who can do steady state exercise at a very high level typically have a very high VO2 max. Now, I mentioned VO2 max earlier. VO2 max is a measurement of somebody's aerobic capacity, and what it is measuring is essentially how fast and in what amount can you deliver oxygen to the muscles, and then how fast can the muscles extract that oxygen and use it to produce energy, okay? VO2 max is sort of composed of your ability to circulate and deliver oxygen and the ability of the muscles to use oxygen, okay? We're going to come back and talk about that here momentarily. Right now, we're going to jump back to the oxygen deficit again. Again, this is going to usually take about 2 to 3 minutes before you transition to aerobic metabolism. So during that 2 to 3 minute time period, you're relying on glycolysis. You're also depleting your body of stored oxygen. You're using up some of your stored ATP. you're possibly using some phosphocreatine, and then you're producing lactate, right? So again, we're creating this deficit where a lot of the oxygen that we then have in our body during the initial minutes of exercise, let's say from minute 3 to 10, we're using that extra oxygen to replenish some of these things, right? We're using some of that oxygen to get rid of some of the lactate that we produced, right? When oxygen is available, when oxygen is available, the lactate that we produce can be split back apart into pyruvate, which can go to the Krebs cycle, and NADH, which can go to the electron transport chain. So you're producing lactate during the first 2 minutes, but once you transition into relying on aerobic metabolism, mostly for the activity, the lactate that you produce can now be used, it can be oxidized, it can be used to produce ATP, okay? So the oxygen deficit is not really a bad thing because the damage that you do, and I use that term relatively speaking, the depletion and the accumulation that occurs during the oxygen deficit usually gets resolved in the first few minutes of your reliance on aerobic metabolism. So it's not really a big deal, right? But again, this does show us why we are often out of breath at the beginning of even easy exercise. And then once we settle into that steady state, our breathing and our heart rate usually drops down a little bit. And that symbolizes the fact that we've now transitioned to being able to rely mostly on aerobic metabolism for energy production. Trained and untrained, we already talked about that. So yeah, the better shape you are in, the more rapidly you can start using aerobic metabolism, and the less of a hole you'll find yourself in once you get going. So why does that occur? Energy systems are more efficient. We kind of talked about that. You have more enzymes in your cells to help produce more ATP. The more fit you are, your body is more efficient at redirecting blood flow. So you're able to get blood flow to the appropriate areas and divert it away from areas that don't need it. We'll talk about that in a later chapter, okay? Those are the two main things that occur. So through these fitness adaptations, your cardiovascular system is more efficient at delivering the oxygen, and your muscles are more efficient at using the oxygen as part of the aerobic energy production process. All right, so let's finish up by talking about VO2 max. So again, this is sort of the gold standard measurement for fitness, right? This was what a lot of early testing in exercise science was really focused on, was measuring VO2 max. We have an online lab that we will do later in the semester. I'm actually the subject for the test, so you'll get to laugh at me watching me kind of exercise to exhaustion on that. I think I'm actually wearing the same shirt in the video too, which is funny. But what does this mean? So, VO2, so the O stands for oxygen, and the V stands for consumption. So the consumption of oxygen at a maximal level, which is where we get VO2 max, or maximal oxygen consumption, okay? So theoretically, when you're exercising all out, your body it has a maximal level of oxygen it can use, okay, to fuel that activity. The higher one's VO2 max is, the higher amount of oxygen they can use, the faster that person can run, just to use running as a great example, okay? And what that is showing is like, yeah, this is your body's maximal capacity for producing energy aerobically. The higher your capacity for producing energy aerobically, the faster you can run, and not really the faster you can run, but I would say the longer you can sustain a high intensity steady state, right? So again, a steady state activity would not be all out. It has to be sub-maximal, but it's how long can you maintain that steady state activity. People with high VO2 maxes can maintain steady state activity for a long period of time, okay? And yeah, so what this is showing us is ability to maintain intense exercise for longer than 4 to 5 minutes, okay? A definition that I like is here because it tells you the energy or the body systems that are included in the consideration of VO2 max. So VO2 max reflects the maximal ability to take in, circulate, and utilize oxygen for energy production. Okay, so let's break this down. The taking in of oxygen is going to involve which body system? The pulmonary or the respiratory, so the lungs. Okay, a good pulmonary capacity means you could bring in more oxygen per breath, etc. Then we have circulate. We have to bring the oxygen in with the lungs. We then have to circulate that oxygen with what system? Cardiovascular, right? So the heart pumping, the blood vessels delivering, all of that reflects the capacity of the cardiovascular system. And then the utilization of oxygen, that occurs where? Where does the actual energy production occurring during exercise? In the muscles, right? No, not these muscles. If you're running, it's your legs. So it's your pulmonary, cardiovascular, muscular. Those are the three body systems where the events are occurring that lead to having a VO2 max. So bringing the oxygen in, circulating and delivering that oxygen, and then using the oxygen to produce ATP, right? So that's kind of summarized right there. I love that definition because, again, it tells you exactly which systems are contributing to aerobic energy production during exercise. Now, as we see in the upcoming lab later in the term, we do a test to measure VO2 max using specialized equipment. And we do what is called a graded exercise test, where we pick a running speed that is the same for the whole test. And we have a series of exercise stages. At each stage, we increase the percent grade. So that's where this is, the incline. So we start out at 3 minutes on a 0% grade at a certain speed. In stage 2, we jump up to 2%, 4%, 6%, 8%. My classes at U of L, we just did this past week. We have student volunteers do it. Again, for our class, I have a video that we filmed and I'm the subject and my graduate assistants are running the test. But it's going to follow this exact same. The goal of a VO2 max test is to then get the person up to their maximal exercise capacity in about 10 minutes. You don't want this test to be very long, because if it extends beyond that, then the muscular fatigue is going to become the issue. You want to really maximize the cardiovascular system. So we'll see that more in a couple weeks when we actually have a lab over this activity. Okay. Last thing, how many more slides do I have here? We're almost done. I need to wrap this up in 3 minutes. The Fick equation. So the Fick equation represents VO2 max. Okay, the Fick equation is here. Now this is something I want you to start learning. The Fick equation states VO2 is equal to Q times a VO2 difference. What does that mean? Well, VO2 we know means oxygen consumption. The Q is the cardiac output. That is the amount of blood your heart beats out per minute. Okay, that is usually expressed in liters per minute or milliliters per minute. The Q is a function of heart rate, which is beats per minute, stroke volume, amount of blood per heartbeat. So those things combine, amount of blood exiting the heart per minute. Okay, and then the AVO2 difference is defined here. So the difference in the oxygen concentration between the arterial blood and the venous blood. Okay, so where would there be less oxygen? Think about that for a second. There should be less oxygen in the venous blood, right? Because the arterial blood is oxygenated blood. Between the arterial and the venous blood supply, we have the capillaries. In the capillaries is where the tissues extract oxygen, right? So the greater the difference, that means the muscles are extracting more oxygen, right? So we can reformulate this equation for VO2 max and just say VO2 max equals Q max times a VO2 diff max. So if you're at your maximal level of blood exiting the heart per minute, you're maximally extracting oxygen from the blood, that's going to reflect what your aerobic capacity or your VO2 max actually is, okay? I'm going to come back and talk about this equation in later lectures. This is just like, again, this is my favorite concept in exercise physiology. If you can understand the Fick equation, you're ahead of the game, okay? But we'll talk about it again in a later lecture. I just wanted to introduce it today. So this is a good figure that kind of shows, again, the systems that are included in aerobic energy production. You know, we have the lungs, cardiovascular system, and then in the muscles is where aerobic energy production occurs. But this is very much, you know, all three of these. If you have a weak link in any one of these, your VO2 max is going to be limited. If you've had a heart attack, your pumping capacity is going to be compromised. Your VO2 max will be compromised. If you have a lung disease, such as chronic bronchitis, even asthma, something along those lines, your VO2 max could be compromised. Okay, so all three of these systems have to be working optimally to have a high VO2 max. Oh, mama. So we have recovery, and then we're done. I want to try to wrap this up pretty quickly. So you probably noticed after you do hard exercise, your breathing does not automatically drop down to resting, right? It stays elevated for a period of time. And the higher the intensity of the activity, the longer your breathing stays elevated. So again, going back to running the 800. If you run the 800, you're probably out of breath for a few minutes after you stop running, maybe even an hour, right? Where if you run for 20 minutes at a very low intensity, your breathing drops back down to resting pretty quickly. Okay, so the intensity of the activity definitely influences the recovery time. Okay. So for light, steady state activity, the recovery time is very rapid. For moderate to intense activity, the recovery time is more prolonged. Okay, and that recovery time is called EPOC. Excess post-exercise oxygen consumption. Okay, so that's the acronym that we use, EPOC. I'm going to jump back here again. These are some EPOC graphs, right? So this kind of shows you light aerobic exercise, we have a very rapid recovery. During moderate to heavy, we have a much longer recovery, okay? And then during maximal exercise, an even slower recovery, okay? So the higher the intensity of the exercise, the longer it takes you to recover from it. And I'm going to give you 5 seconds to think about why that is. What are we accumulating during intense exercise that makes recovery so much more difficult? 5, 4, 3, 2, 1. If you said lactate, you got it, right? Lactic acid is a lot of times the answer to this. During light aerobic activity, there's very little lactate accumulation, if any, so we recover very rapidly. During moderate to heavy exercise, there is a larger lactate accumulation, so this recovery is often delayed somewhat because we have to deal with the lactate that we produced, okay? And during all-out activity, it's a similar idea, is that we've accumulated this lactate. After we stop exercising is when we have to deal with this lactate, so that's why our breathing stays elevated. That's why we're consuming excess amounts of oxygen post-exercise, even though we're no longer exercising. So what are we doing during this period? This section of the slide sums it up pretty well, right? You're replenishing things that you depleted during the exercise, and also removing things you accumulated during the exercise. So during exercise, we deplete, and I said this earlier, we'll say it again, stored oxygen. We keep a very small amount of oxygen stored in our blood and muscles. That can be depleted during exercise. We have to replenish that. Well, how do we do that? Well, we breathe in extra oxygen after we stop exercising to replenish that. We have stored ATP that we've used. We have to replenish that. Well, how do we do it? We use aerobic energy production to make more that we then store, okay? We might have depleted our other phosphates, phosphocreatine, so we can use the ATP that we're making post-exercise to replenish our phosphocreatine stores, okay? We then have ATP. Sorry, that's not what I meant to say. We then have lactate that is accumulated that we have to get rid of, okay? Now, if the aerobic energy system is operating at a higher level, it's going to require input, okay? So what we can do is we can take that lactate that we produce during exercise, break it back down into pyruvate in NADH, and then send those products into the aerobic energy system to make ATP to replenish all those things that we just talked about, right? So we can take lactate, recycle it, and ultimately replenish things that were depleted during exercise, okay? So again, the more lactate you accumulate during the activity, the longer this process takes. Versus light exercise, you don't accumulate as much lactate, so this process is much, much faster, okay? So here we go, two factors that impact recovery of VO2, the level of glycolytic energy production during the activity, and then also, some other factors that we're not going to touch on today, but the more your body heat elevates during the activity, the longer your recovery period is as well. So if you ever exercise outside in the summer, you notice that it takes you longer to recover from that activity, okay? Because your body has to sort of mitigate that body temperature increase. All that heat that accumulates in your body, we got to get rid of that. We do that by breathing, sweating, etc. Okay, so there's other factors in addition to lactate that can influence recovery as well, but we'll just focus on that one mostly for today. Again, this just shows us that the longer the activity is, also the higher the EPOC level is. And again, the longer something lasts, the more of that depletion and accumulation that occurs, the longer it's going to take to undo that stuff in the recovery period. Okay, and this is a good last slide that kind of shows, again, all of the things that have to be done post-exercise. Replenishing ATP PCR, getting rid of lactate, oxidizing the lactate, restoring oxygen levels in the blood, I mentioned that one, getting the temperature back down. The fact that you might have these hormones, like the stress hormones that increase in concentration during exercise, they're going to stay elevated in your body for a little bit post-exercise. That's also going to influence your metabolism to stay elevated, your breathing to stay elevated, etc. Okay, so, and again, intensity, the higher the intensity of the activity, the larger the magnitude of these things are, so the longer the recovery period will be, okay? Now, last thing here, I promise this has gone pretty long, but this is a pretty important chapter. Recovery is faster when done actively, right? So instead of just sitting down to recover from hard activity, you want to stay moving, right? So this graph shows us passive recovery is in the green, high intensity recovery, no, low intensity, moderate intensity. So the yellow is going to be the fastest dropping time, right? So the optimal intensity, as we see here, for exercise to recover rapidly is around 35% of VO2 max, okay? You track athletes in the class, you do this all the time without thinking about it, right? You have multiple events in one day. After your first event, you need to recover for your next event. Do you just sit down? Does your coach let you sit down? Hopefully not. They tell you to walk, light jog, just stay moving. Football players, the same thing, right? When you're a defensive player and you've been on the field for a whole series, you don't just go stand on the sidelines. You get on a bike and cycle, right? Especially if you've been on the field for a long period of time. You need to stay moving because that actually, not only does it keep your body temperature elevated, and that's good if it's cold, that can help pull your lactate levels down. So when you get back on the field, you're ready to go at it full force, okay? So active recovery is better, but the intensity has to be low because if it gets higher, you run the risk of starting to produce more lactate or delay lactate clearance. And the whole point of recovery is to clear the lactate. So active recovery to low intensity, roughly 35% is what is recommended. That is going to make this process occur at a faster level, okay? So that is it. Here's our summary. Got a few things. So your tasks, again, we do have lecture study questions this week. We do not have a critical thinking assignment because of the exam. The exam is this week as well. This chapter is not included on this exam. This chapter will be on the next exam. I will make the exam available to you on Wednesday morning at 8 o'clock, and it is due by Friday the 9th at 8 p.m. So you can take it anytime during that period, but once you start it, you have to finish it. So make sure you dedicate some time to sit down for, give yourself an hour and a half. I put a 75-minute time limit on the test, which is a standard class time. Maybe you need that long, maybe you don't, but give yourself a couple hours just to make sure that you have plenty of time to sit down and finish it. All right? So I will talk to you all soon. Bye bye.